Hello everyone, today I will be talking about storm surge, from its simple definition to its physics, and how we can make use of math to understand the reason behind the variation in sea level. Let's start with the definition from the UK Met Office. Storm surge is defined as the change in sea level caused by a storm, and it is due to the high winds pushing the seawater towards the coast, causing it to pile up there. Some of the impacts of the storm surge are flooding, saltwater intrusion, and coastal erosion. Now, let's move on to a case study and take a look at these two typhoons. We are going to learn about their impact on Hong Kong. First of all, this is the Typhoon Hagupit. It was a strong typhoon that passed near Hong Kong in 2008. According to the Hong Kong Observatory, its closest approach to Hong Kong was around 200 km, and its center's maximum sustained wind during its closest approach was around 170 km per hour. For this one, it's the Typhoon Zhengzhu in 2006. Similar to Hagupit, its closest approach to Hong Kong and its center's maximum sustained wind was also around 200 km and 170 km per hour. From their similar distance and maximum wind speed, how would you expect their storm surge to behave? Are they going to be similar? According to the record, the maximum storm surge above the astronomical tide for Hagupit was 1.77 meter, and Zhengzhu was 0.77 meter. The other record also showed that Hagupit led to a higher storm surge than Zhengzhu. But why? Why are they so different? To have a better understanding, let's take a slightly more in-depth look at storm surge. Like how we understand other phenomena, we first simplify the situation by setting some assumptions. Assume that the wind is parallel to the coast with no x variation and no friction. The momentum equations can be written as these two equations, where there will be no pressure gradient along the x direction as we assume no x variation, and there will be no wind stress along the y direction as we assume the wind is parallel to the coast. Right after the momentum equations, of course, we are going to set up the continuity equation. Since we assume no x variation in the sea level eta, the equation can be simplified as shown here. Now, we successfully have three equations with three unknowns, which we can easily solve one by rearranging the equations. Let's start with the cross-coast velocity v, by taking the time derivative of the equation and sub in the rearranged x-direction momentum equation and a differentiated continuity equation. We can end up with this second-order non-homogeneous partial differential equation of v, but let's forget about its mathematical name. It's actually a forced shallow water equation. Although the solution of this equation should be a combination of its steady and transient parts, let's only consider the steady part where there is no time variation, as it dominates the motion after a period of time. We can have the solution in this form, where A is the Rossby radius. By the solution of v and the continuity equation, we can solve for the sea level eta as a function of y, the offshore distance, and time. We can see that the sea level variation is caused by the wind stress, which matches the definition from the Met Office, decaying exponentially over an offshore distance normalized by the Rossby radius and changing linearly with time. Of course, we can also solve for the along coast velocity. However, it is not our main focus today, so we will skip it for now. To interpret the process, we should start with the cross-coast velocity. The solutions tells us that the motion is caused by the Ekman transport, where the velocity increases from zero at the shore to steady Ekman flow far away, and is flowing towards the coast when the wind stress is positive. Then, the continuity equations tells us that the further and faster water motion towards the coast must lead to water piling up over time, or if the wind stress is negative, the water will be removed from the coast. Now, let's visualize the process. Assume we are in the northern hemisphere and the typhoon is moving to the west of the city. The wind stress is now parallel to the coast. By balancing the wind stress and the Coriolis force, like how we set up our momentum equation, we can obtain a flow towards the coast. Therefore, based on the sea level solution we obtained, we can expect a pattern like this, with the Ekman flow slowing down towards the coast and the majority of the uplift is within the Rossby radius. However, when the typhoon moves to the east of the city, the wind blows off the coast, and the balance is like this. The water flow is parallel to the coast, so we can expect much less water to pile up, and therefore a weak to non-storm surge. Back to our original question, why were these two typhoons so different? Here are the typhoon tracks, where we can see that Hagupit traveled to the west of Hong Kong and Zhengzhou traveled to the east. Schematically, these were how the water flowed and caused different levels of storm surge. Therefore, it is important to predict the path of the typhoon or hurricane to evaluate the possible impact of the storm surge. Thank you for listening, and that's all for my presentation. I hope you can learn something from watching my video. Bye!